We have talked so far entirely about beta minus and beta plus emission and have ignored the third type of beta transition, which is actually the orbital electron capture. In fact, the capture of orbital electron by nucleus is also a type of beta transition, and this transition was first of all suggested by Yukawa and Saketa. And finally, later on, this process was discovered by a great scientist L. Alvarez. In fact, it is seen that if the nuclei have high Z value, that is a high number of proton, then the Coulomb barrier is very high, and this high Coulomb barrier tends to prevent the emission of positron. You know that positron is emitted in case of when Z value is in fact larger than required for the stability. But if this Z value is very large, Coulomb barrier is also very large and that very large Coulomb barrier prevents the emission of positron. Okay, but in this condition another phenomenon actually takes place. And what is that another phenomenon? Actually, in this condition, when the Coulomb barrier is very high and positron emission is not possible, then actually proton gets converted into neutron, but by a different process, and that very process is actually called electron capture. Actually, what happens in this electron capture? In fact, the orbital electron or the electron present in the cells of the atom are captured by the nucleus, and after capturing of electron by the nucleus, a proton is converted into a neutron and a neutrino. You can see I have mentioned that process here. This is your proton, and this electron has been captured from an atomic cell by the nucleus, and after this capturing, this proton is converted into neutron, but at the same time a neutrino is created and emitted. So this electron capture is simply the capture of the atomic electron by the nucleus, and after that a proton is converted into a neutron. So this is just a beta transition process. Okay, actually you know that according to the cell model of atom, the electrons are distributed in different cells, and the first quantum level, which is called K level or K cell, is actually closest to the nucleus. So the probability of capturing of electron present in the K level is highest. So normally in general form, the electron present in the K level or the first quantum level gets captured by the nucleus. But often it is seen that the electron present in L level is also captured, but that happens occasionally, not regularly. This is not a common phenomenon. The common phenomenon is what? That is actually the capture of electron present in the K cell by the nucleus. So normally when you talk about the electron capture, then normally we think about the capture of the electron present in the K cell. But you can't ignore that the electron present in L cell and or other higher cell will be not captured. That also takes place. In fact, when the electron present in the K cell gets captured, then it is called K capture. And if the electron from the L cell is captured by the nucleus, then it is known as L capture, and so on. Okay. Now, what will happen when this electron capture process will take place, how the atomic number and how the mass number will be affected? You can see by this reaction. I have actually assumed here that this ZXA is the parent nucleus, and this nucleus captures an electron, you can see, and after capturing this electron, you know that a proton will be converted into a neutron. So what will be the effect on the total number of nucleons, that is the mass number? You can see that will not change, because now in the daughter nucleus, you can see there is a decrease in the number of proton. So the new number of proton in the daughter nucleus will be Z minus 1, because one proton has been converted into neutron. On the other hand, the number of neutron is increased by 1, so this will become n plus 1, and so the total number of nucleons in the daughter nucleus will be what? This will be Z minus 1 plus n plus 1, that will be simply equal to Z plus n, and that is equal to A. So after this electron capture, there is no change in the mass number of the daughter nucleus. But as the number of proton is decreased by 1, so the charge number of the daughter nucleus will be Z minus 1 if the charge number of the parent nucleus is Z. And as you know, in this process, a neutrino is created and emitted. Okay. So you can see that after this EC process, the identity of the parent nucleus is changed because its charge number is changed. Okay. In fact, in this reaction, again the energy will be evolved, which is called actually the Q value of energy. In fact, as in the product, there is a daughter nucleus which is very heavier, and there is a neutrino which is almost massless, its rest mass is 0. So due to the very large mass, this daughter nucleus does not share any energy. Almost negligible energy is imparted to this daughter nucleus during its recoil. So you can say that in electron capture transition, the total energy is carried out by this neutrino. Total energy will be carried by this neutrino. Okay. As you have studied earlier, that in the beta plus decay process, that this process only occurs when at least the available energy is twice of the rest mass energy of the electron. Okay. But in case of the electron capture, this requirement is not necessary. It means EC often occurs when beta plus decay cannot take place. So even then the electron capture takes place. And as I have told you that the total energy evolved in this process is carried by the neutrino. So what will be the kinetic energy of the emitted neutrino? You can think about it. Actually, the kinetic energy of the emitted neutrino is given by this formula. You can see this is E nu. E nu is the kinetic energy of the emitted neutrino, and that will be equal to E naught plus MEC square minus EB. Now understand how this expression actually represents the kinetic energy of the emitted neutrino. You know that the Q value, this E naught is actually the difference of the rest mass energy of the parent nucleus and the daughter nucleus. Okay. And apart from that, there is an electron captured by this daughter parent nucleus. So this is rest mass energy of the electron which is actually captured. But this EB is what? This is actually the binding energy of the electron present before the capture in a particular cell. So you know, if any electron present in a particular cell will be actually transferred from that cell to another place, definitely an energy is required to break the stable state of that electron, and that energy is actually equal to its binding energy. So if you want to find the kinetic energy of the emitted neutrino, that will be equal to the difference of the rest mass energy of the parent nucleus and the daughter nucleus, which is E naught, plus rest mass energy of the electron and minus binding energy of the electron in the respective cell. It means if the electron is captured from the K cell, then this EB corresponds to the binding energy present in the K cell. And if the electron of the L cell is captured, then this EB is actually the binding energy of the electron present in the L cell before the capture. So actually this E naught and MEC square, these two terms will remain always same, but the value of EB will depend on the cell from which the electron is captured. So E nu is different for the neutrino when there will be either K capture, L capture, and so on. Okay, I have already mentioned these things here. You can see this E naught is what? This is mx minus my times c square, where mx is mass of the parent nucleus, my is mass of the daughter nucleus. Okay, so this E naught is the difference of the rest mass energy of the parent nucleus and the daughter nucleus. And as I have told you that this EB is binding energy of the electron in its respective atomic cell before being captured. Okay, and MEC square, you know, this is rest mass energy of an electron. Okay, and as I have told you that due to the heavier mass, the daughter nucleus share almost no energy, or you can say a negligible amount of energy is given to the recoiling of the daughter nucleus. Okay, now you can see that E nu is not same for different electron capture. So as you know that this EB will be different for different cell. EB will be actually highest for K cell, okay, because the binding energy corresponding to the K cell will be highest, and this EB will be relatively smaller for the L capture. Okay, so this EB is different for the capture of electron from different cell. So actually, as EB varies for the capture of electron for different cells, so the spectrum of the neutrino energy is observed in this process, and this will be actually a line spectrum. You can see if we will represent the energy of the neutrino on this line, let us say E nu, then for the K capture it will be in fact a smallest. For L, that will be greater than greater than that of the K cell. So this is for K, this is for L. So actually the energy spectrum for the neutrino energy is observed if capture takes place from more than one cell, then the energy spectrum will be a line spectrum. Okay, So this was some of the basic fundamentals of this electron capture. Now we will see the proper theory or a rigorous theory of this electron capture. In fact, the theory of electron capture is just similar to the ordinary beta decay, but there is some difference between the theory of an electron capture and the theory of beta decay. And what is that difference? You can see it. Actually, in case of this electron capture, you know that the electron has a definite energy state, but in beta decay process you have seen that the energy spectrum of electron was actually a continuous spectrum, that is a continuous curve you have obtained. And so in the beta decay process, actually energy of electron varies from 0 to a maximum value, but in this electron capture process the energy of electron is actually constant. Okay, and at the same time the electron wave function is actually in this case atomic wave function. This will be just atomic wave function. So you will see that the electron wave function in this case will be not represented by the plane wave, but it will be just represented just like a bond system like hydrogen atom or hydrogen like atom, and the wave function will be just that atomic wave function. Okay, so this is the difference. In beta decay process, the wave function for the emitted electron was just a plane wave, but in this case this will be a wave function just like a wave function for a hydrogen like atom. Okay, now the same formula for the transition probability per unit time will be used in this case. Okay, so I have mentioned here that the transition probability per unit time corresponds directly to the decay constant as it was in case of the beta decay process and for this orbital electron capture. And you have definitely, you can remember, you have already studied the process of beta decay and you have seen that the decay constant, which is actually a reciprocal of the mean life of beta decay process, this is given by 2 pi by h bar and a square of the modulus of integral psi I star hif psi f d tau times dn by d e nu. This formula I have written here directly, but you have seen this formula, how this formula is actually obtained in the previous lecture on beta decay process. Okay, and you know that this HIF, this is actually the transition matrix element. Okay, and what is this dn by d e nu? You know, this is actually the density of neutrino states. What does it mean? It means if you say that in the energy range of neutrino d e nu there is actually the dn quantum states of the neutrino, then for the unit energy range this will be equal to dn by d e nu. So this is actually the number of quantum states of neutrino for the unit energy range. Okay, now actually this interaction matrix, that is HIF, this is exactly same as in case of beta decay, and you have already obtained the value of HIF in case of allowed transition in case of beta decay. So I will write here the expression which we have already derived in the previous lecture on beta decay directly. So you can remember, and if you have not watched the video on the beta decay process, then you must watch first of all that video, and then you will see that how this expression has been obtained there. So you have seen that this mod of HIF square is equal to g square times mod of psi E0 square times mod of psi nu 0 square times mod of MIF square. In fact, you know this G is actually called coupling constant. And what is this MIF? You know, this is a dimensionless matrix element, or you can say this is just a scalar and it acts like an operator. Okay. Now, in this case too, just like the case of beta decay, the neutrino wave function is just a plane wave, and so I have written here that psi nu of r, this is n nu e raised to the power I over h bar p nu dot r. In fact, here this n nu is the normalization factor, okay, and p nu is the momentum of the neutrino, and r is actually the space coordinate. Okay. Now, in the when you have studied actually the beta decay process, then you have assumed that there is a large box whose volume is V, and assuming that large box, you have used the normalization condition, and after using the normalization condition, you have obtained that the value of this normalization factor is 1 over root V. I have not calculated the value of n nu here because you have already calculated this normalization factor in the lecture on beta decay. So I have written it here directly. You can remember. You have watched the video, and so you can remember it. So n nu is equal to 1 over root V, where actually V is the volume of a big box. Okay. Now, you can see if we consider that the neutrino is present in the nucleus, and nucleus is assumed at the origin. So for the nucleus, R is equal to 0. And so when the neutrino was created inside the nucleus, then what will be this wave function psi nu 0? You can see when we will take R equal to 0, this exponential factor will be 1 because there will be e to the power 0, and that will be equal to 1. So in fact, in that condition, this psi nu of 0 will be simply equal to 1 over root V. Okay. So you have calculated the value of psi nu of 0. Now we will calculate the value of psi e of 0. As I have told you earlier that the electron wave function in this case is different from that of the electron wave function in case of beta decay. Because in case of beta decay, you have seen that electron wave function is also actually a plane wave. Why? Because just like neutrino, as neutrino is created and emitted from the nucleus, in beta decay process, you have seen that electron is also created and emitted from the nucleus. But in this electron capture case, electron is already present in a cell, and that electron is captured by the nucleus. Actually, when the nucleus captures the electron, that nucleus, after capturing an electron, behaves just like a bond system, or it just behaves like a hydrogen-like atom. So in this case, we will represent the electron wave function simply by the wave function which is used for hydrogen-like atom. Okay. And you know that for a hydrogen-like atom, for different quantum states, the wave function is different. So here we will consider the capture of electron from the K cell. Particularly we consider that electron in K cell is captured. So if you consider that electron of K cell will be captured, then for a good approximation for the K electron, we can take the wave function 1s state of hydrogen-like atom with the charge number of the parent nucleus. It means in this condition we will consider that there is an atom and it is in 1s state, and its charge number, that is number of proton, is same as that of the parent nucleus. Okay, and you have definitely studied in quantum mechanics the problem of hydrogen atom, and for the 1s state, what is the wave function? The wave function I have written here psi e k. K actually refers that the k electron has been captured, and that is simply equal to psi s. Psi s means this is wave function for the 1s state. And remember, if you have studied the problem of hydrogen atom, then you can see that this psi s is equal to 1 over root pi times z over a naught whole to the power 3 by 2 times e to the power minus zr by a naught. You have to remember it. This result I have written here directly, and this is the subject matter of the problem of hydrogen atom of quantum mechanics, and you can see any standard textbook on this subject, and you will find this formula there. Okay, in fact, in this formula, this a naught is actually Bohr radius. Okay, Bohr radius means this is actually the radius of the first orbit of the hydrogen atom, and this Bohr radius is given by this expression. This is 4 pi epsilon naught h bar square over me times e square. Okay, this is the expression for Bohr radius. Okay, now see, in our expression for the transition matrix HIF, there is psi e of 0. It means we will find the value of this psi e when r will be equal to 0. Okay, and when r will be 0, you can see this exponential factor will be e to the power 0, and that will be 1. So psi e of 0 will be simply equal to 1 over root pi times z over a naught whole to the power 3 by 2. Okay, so you can see I have mentioned it here that psi e k of 0, that is psi e of 0, is simply equal to 1 over root pi z over a naught whole to the power 3. Not 3 but 3 by 2. This is 3 by 2, not 3. Okay, so this is 3 over 2. Okay, now we have obtained the value of psi e of 0 in this equation 7, and you can see the difference that this is not a plane wave, but this is just a hydrogen-like atom's wave function. Okay, and you have obtained the value of psi nu of 0 here in this equation, and so now we will substitute the value of psi nu of 0 from this equation 5 and psi e of 0, which you have just obtained, in this equation number 4, and then we will get actually the value of this transition matrix elements modulus square, and what will be that value you can see. And actually I have substituted this value, these values in this equation. In fact, in this equation 3. Okay, so when we will substitute the value of those quantities, not in 3 but what is that equation? HIF. Yes, in 3. In fact, in equation 3, the integral, sorry, the page has been turned, but don't worry, this will be just okay. there is some problem in this device, so normally anytime page gets turned, so don't mind it. You can see here. So when we will actually substitute all these values in this equation, then you can see that the decay constant, I have written here decay constant lambda k because we have considered the wave function psi e for the k capture. So a subscript k has been used here. So when you will use the expression for lambda and substitute all the values which we have obtained just now, then you can see that this lambda k is simply equal to 2 pi over h bar times g square, and for that integral, actually for that integral we have written here g square mod of psi e 0 square times mod of psi nu 0 square plus times mod of mif square times dn by de nu. Okay, now substitute the value. 2 pi over h bar times g square is at is, and for mod of psi e 0 square I have written here 1 over pi times z over a naught whole to the power 3, because you can see psi e of 0 is this much. It is defined in equation 7. So when you will square it, this will be 1 over pi z over a naught whole to the power 3. And you have seen that actually this psi nu of 0. You have seen earlier that this psi nu of 0, this is equal to 1 over root v. And so when we will square it, this will be simply 1 over v. Okay, and times mod of mif square times dn by de nu. Okay, now you can see that this pi and this pi will cancel out, and our result will be lambda k equal to 2 over h bar times g square times z over a naught whole cube times 1 over v times mod of mif square and times dn by de nu. Now we will finally calculate the value of this dn by de nu, and you know this dn by de nu is simply the density of neutrino states or number of quantum states per unit energy range for the neutrino. This is actually also called a statistical factor because it is calculated by the concept of phase space in statistical mechanics. So this is also called a statistical factor. Okay. One thing is here different from that of the beta decay process. In fact, when we have calculated this statistical factor in beta decay process, then actually we have calculated dn by de nu and dn by dee, that is for both electron and neutrino. But in this case, as you know, in case of electron capture, the electron has definite energy. Electron's energy is definite. So there is no need to find the value of dn by de nu for the electron because the electron's energy is definite. Okay. So this dn by de nu is solely determined by the neutrino energy or momentum. Okay. So you can see how this dn by de nu will be calculated. Actually, while discussing the beta decay process, I have discussed this result in very detail. In shortcut, I am just repeating that thing here. You can see. Actually, in phase space, or you know, the volume in phase space, if you consider that the volume is in phase space is delta gamma, then this delta gamma is equal to volume of configuration space, which is actually here V, at times volume of the momentum space. Volume of the momentum space. I am writing it by this tau. And what will be this tau? In fact, if you consider that the momentum of the neutrino lies between P nu and P plus dP nu, then this tau will be simply the volume of the shell lying between two spheres having radius P nu and P nu plus dP nu in momentum space. So volume in phase space is equal to volume in geometrical space or configuration space times volume in momentum space. And what will be this volume? You can see this volume is simply equal to 4 pi P nu square dP nu. Okay. So the volume in phase space will be equal to V into 4 pi P nu square dP nu. You can see it here. Now, you know that in H cube volume, the number of quantum states is 1. In volume H cube, number of quantum states is 1. So in unit volume, what will be the number of quantum states? This will be 1 by H cube. And so, in this much volume, what will be the number of quantum states? That will be simply equal to 4 pi nu square dP nu divided by H cube. Okay? Divided by H cube. And times V, because in volume, in phase space, the total volume will be equal to V times 4 pi P nu square dP nu, and in one quantum state the volume corresponding to the one quantum state is H cube. So in this much volume, the number of quantum states, that is dn, which I have written dn nu, that will be equal to this much. Okay. As I have told you that in this case the number of quantum states mean number of quantum states of neutrino, because electron has a definite quantum energy and so its quantum state will be definite. So we have to consider only the number of quantum states of neutrino. Okay. Now you know that the momentum of neutrino P nu is equal to E nu by C, because its rest mass is 0, just like photon. Okay. And so dP nu is equal to dE nu by C. So now we will change this P nu by E nu by C and dP nu by dE nu by C. So after making this substitution, what will be your result? You can see this will be V into 4 pi E nu square dE nu divided by C cube times H cube. Okay. And therefore you can find that dN by dE nu, that will be equal to 4 pi V E nu square over C cube times H cube. Instead of H, I have written here 2 pi H bar. And so this is 2 pi H bar whole cube. And so dN by dE nu, this is simply equal to V times E nu square over 2 pi square C cube times H bar cube. Okay. So in this way we have calculated this statistical factor, that is the number of quantum states per unit energy range for neutrino, or the density states of the neutrino. Now we will substitute this value of dN by dE nu in this equation. You can see in this equation we will actually substitute this value. Yes, in this equation 8. This equation 8. Substitute this value. So instead of dN by dE nu, we will write the expression which we have just obtained and see, then you will get the value of lambda k. So what will be this lambda k? You can see this lambda k will be then 2 over h bar times g square times z over a naught whole cube times 1 over v times mod of mif square times dn by dE nu, and the value of dn by dE nu, you can see this is this much, and substitute this value here. Now this v and this v will cancel out, and again you know that the Bohr radius a naught is equal to this much. Remember this expression. This is 4 pi epsilon naught h bar square over me times e square. So now in this expression we will substitute the value of this Bohr radius a naught, and after substituting that expression, what will be our result? You can see this is lambda k equal to 2 over h bar g square times z cube times 1 over a naught cube. So this is the value of 1 over a naught cube. Okay, and this is the remaining factor, you can see. Okay, now after simplification you will get lambda k equal to this much. This is actually g square z cube me cube e to the power 6. You can see the algebra, and divided by 64 pi to the power 5 epsilon naught cube h bar to the power 10 c cube times mod of mif square times e nu square. Okay, but as you know that in a K cell there are actually 2 electrons, not only 1 electron. K cell is filled with 2 electrons. So in fact in this condition, as the K cell contains 2 electrons, so we have inserted a factor 2 to take account the presence of the 2 electrons in the K cell. So I have multiplied here by the factor 2, taking the 2 electrons of the K cell under account. This expression for lambda k must be multiplied by 2. So after multiplying by 2, we will get the value of lambda k equal to this much. Okay, this will be g square z cube me cube e to the power 6 over 32 pi to the power 5 epsilon naught cube h bar to the power 10 c cube times mod of mif square times e nu square. So this is actually the expression for the decay constant when we consider actually K capture. Now you can see this expression that this lambda k is directly proportional to z cube. So if z is large, then lambda k will be also large. It means this relation shows that the decay constant is larger for the heavy elements, that is the elements whose charge number or atomic number is large. The decay constant will be also large. Okay, now actually this matrix element MIF is same for the electron capture and for the beta decay process. There is no difference between the value of this MIF for the electron capture process and the beta plus decay. Okay, so if you calculate the ratio of lambda k and lambda beta plus, lambda k is already defined here. You can see in this equation, in fact 10, but lambda beta plus we have studied earlier. So when you will substitute the value of lambda k and lambda beta plus, then you will get this result. This ratio is this much. You should remember it. This will be e to the power 6 z cube times e nu square over 16 pi square epsilon naught cube h bar cube c to the power 7 m e square times a function of z and e naught. Okay, this will be the result. This is the ratio of lambda k and lambda beta plus. actually when the value of this ratio of lambda k and lambda beta plus is measured from the experiment, then it is seen that the experimental value agree with this theoretical result. And since the experimental value resembles or experimental value of this ratio agrees with this expression for this ratio, it means this relation is valid, this is experimentally correct. So the theory which we have developed here is actually validated by the experiment. So we simply say that the experimental value of lambda k by lambda beta plus agrees with this equation 11, which validates the theory of electron capture. Okay. Now you know neutrino is not practically observable. Actually, it is practically unobservable. You can't observe neutrino. You can't feel neutrino in observation in an experiment. So, as a neutrino cannot be observed in practice, so how we can think that electron capture has been taken place? In fact, this electron capture is only experienced by observing that there is a disappearance of electron in the K cell or in the L cell. When it is seen that the electron present in K cell has been disappeared, it means that electron has been captured by the nucleus, and this electron capture process has been taken place. So I have mentioned here that as neutrino is practically unobservable, so that the only way to detect the electron capture in practice is to observe the atomic processes following the disappearance of the K or L electron. It means when we observe that the electron present in K cell or the L cell has been disappeared, it means electron capture has been taken place. Okay. So this is the basic theory of electron capture. In fact, you know, when the electron of K cell will be captured, then that vacancy of electron is filled by the electron of the higher cell. Okay. And in this condition, X-rays are emitted. I have not written it here, but you should know that the vacancy created in K cell will be filled by the electrons present in the higher cell, and the extra energy released in the form of electromagnetic radiation, and the wavelength of that electromagnetic radiation falls in the range of 0.1 angstrom to 100 angstrom, and that is the range of the wavelength of X-ray. So in this condition, actually the X-ray is also produced. Okay, and this is actually also called Auger transition. Okay, so I hope you have understand the process of electron capture, which is just a type of beta decay process. So after this electron capture process, now our beta decay theory is completed, and we will see the other concept in our forthcoming lecture regarding this beta decay, like parity violation in beta decay process, selection rules in beta decay process. Such lectures you will find in the forthcoming lecture.